Assalamualaikum, selamat pagi. Boleh dengar suara saya?
Dengar, doktor.
Boleh.
Okey, tunggu yang lain dulu. Boleh confirmkan tak? Boleh tengok slide?
Doktor.
Nampak
Nampak.
Slide bergerak Tak ada apa ni beku dekat mana-mana slide
Tak ada, doktor.
Okay. Alright. Okay, class. It's 9 AM already. So I know that some of you still struggling to enter the Google Meet session. Saya cakap pelat sikit lidah saya kena rasa sakit. Saya bukan makan asam, tak. Saya bukan makan asam. Lidah kena rasa, jadi dia pelat sikit So welcome to the class of solid state physics. It is quite different from the physics that you have learned before. The physics you have learned in your SPM or matriculation or even in the first year, they are known as classical physics, physics classic. So classical physics is only can be used to explain things in macroscopy, big things, big materials, big items. For example, human, cats, even pebbles, rocks. We can explain their behavior using classical physics. For example, you throw a rock from the top of the building and it comes down. We can explain the motion of the rocks from the top of the building to the ground using classical physics, using the kinematics equation that you have learned before. The S equals to UT plus AT square. What else? The V square equals to U square plus 2AS. And so many equations of kinematics. We can use kinematics, normal physics that we have learned before. But once you reduce materials or any objects into very fine particles, usually in the dimension of nanometers, it's 10 to the power of negative 9. That is nanometer times 10 to the power of negative 9 meter. That's all. So these materials or these particles, they can no longer being observed or being explained using classical physics. We need new concept of physics, which is known as quantum physics. Whenever materials or particles, the size become very small, in nanometer size or even smaller, we cannot use the kinematic equation to explain their momentum or their velocity, their speed, their acceleration cannot be explained by kinematic equation, which belongs to the classical mechanics realm. We need quantum mechanics. So we will explore this new concept of quantum mechanics, where particles behave like waves. You know, particles, we have our objects in front of us. These objects, they are known as bulk. They are very big. They can be explained by classical mechanics. Any equations that you have learned before in physics, the velocity, the acceleration, the weight, the momentum, what else? Anybody? What else have you learned before? The thermodynamics. Apa lagi? The resistance, the conductivity, they belongs to classical mechanics. So if you reduce, look into, zoom into this material, this item, we could see that it is made out of atoms. Okay, and before atoms, it might have amorphous materials or crystal materials. Zoom in, we can find its atom. So the behavior of atom inside this bulk thing cannot be explained by classical mechanics. The momentum, the weight is no longer can be termed by the F equals to ma, S equals to ut plus F squared. No, they no longer use that equation. Saya cakap slow sikit, sakit mulut. So we need this new concept of quantum mechanics, which the particles are known as the electron, proton, neutron, and even the atoms. They are known as particles, but they behave like waves. So they have this duality of properties. It can behave like particles, it can behave like waves. And where our classical intuition completely breaks down, we cannot use classical mechanics anymore. The normal physics you have learned cannot use anymore for electron, proton, neutron, atoms, or amorphous clumps of amorphous materials or crystals, atomic crystals. We cannot use classical mechanics. We have to learn the quantum mechanics or quantum physics, because you are material technologists, material physicists. You have to learn solid state physics, which a part of it you have to learn quantum physics. So quantum physics for small things, classical mechanics for bulk things that you could see using your naked eye. Anything that you cannot see using your naked eye mostly belongs to quantum mechanics. For example, bacteria, no, bacteria is still classical mechanics. Viruses also classical mechanics, even though we cannot see using our eye, but they are classical mechanics. Quantum mechanics, mostly atoms, molecules, some of clump of amorphous or crystal material. So now this chapter is foundational. So our class today is 1 hour, right? 1 hour. So this chapter is foundational, is fundamental. Okay, everything in solid state physics, including the band theory to semiconductors. I know that you find that this is so many jargons. Actually, we have a function. If you look at your Google Meet, there is function of Gemini on the top right hand corner. You could see there is star icon, star. Bintang macam ni, bintang macam ni. Bukan macam ni. This is Illuminati, no, this one. Star like this. You click that one and ask the Gemini, what is band theory? What is quantum mechanics? I think you can use Malay also to ask the Gemini. It will give you the definition of the jargons that you've met. So what is band theory? We have specific topic for band theory later. From band theory to semiconductors, which builds this quantum mechanics concept. So let us look at slide number 2. These are the learning outcomes and the motivation to learn quantum mechanics or quantum physics or solid state physics. And let me walk you through what you will achieve by the end of this chapter. So by the end of this 1 or 2 weeks, you should be able to, the first one, describe the de Broglie. It's not de Broglie, not de Broglie. It's de Broglie. De Broglie, I don't know what happened to this Mat Saleh. De Broglie patutnya D-E-B-R-O-Y. I can never mind. It's their name anyway. Describe the de Broglie hypothesis. and calculate the de Broglie wavelength for particles. So what is de Broglie wavelength? What? Okay, you have understood that small particles, they could behave like wave, they could behave like solid particle. So the wave part of the particle, the small particles, can be defined by this de Broglie wavelength. But what is its function? Later we will discuss later. This is just for the introduction. So the de Broglie wavelength is crucial because it explains why electrons and materials behave as wave. So small particles, they behave like they could oscillate, certain oscillation. Small particles, proton, electron, neutron, atoms, or even crystals, or even molecules, they behave like waves. So they have this wavelength and they have their own frequency. They have their own frequency. They could rotate, they could translate, they could move around, and they could vibrate. So they have certain frequency. And frequency is correlated to the wavelength. And the wavelength of these small particles known as de Broglie wavelength. So this is the basic things, the building blocks for you to understand before we move to chapter 5, which we'll learn about the band theory. So band theory is very important for you to understand semiconductor materials. I believe some of you maybe already took the semiconductor devices course. Mungkin. I don't know much about your curriculum structure, maybe. But anyway, you should be able to understand semiconductor material if you learn solid state physics first. Okay? Semiconductor, inside semiconductor, they have band gap. To learn band gap, you have to understand band theory. To understand band theory, you must know what is de Broglie wavelength. Itu dia punya apa jalan cerita. Ini kesinambungan. Right. Now, second, you must be able to explain wave-particle duality. Wave and particle duality. The solid part and also the wave part. Small particles, proton, electron, neutron, we have particle duality. The wave part, also the solid part. You must be able to explain the wave and particle duality for both light and matter with key experiments. You don't need to do the experiments, but you will learn the experiments that have been made by previous researchers. This concept is quite mind-bending, but important. Quite mind-bending because usually we cannot see this quantum mechanics phenomena. That's why we cannot imagine, but we need to learn and try to imagine using our own imagination because we cannot see. We only can see using special instruments, for example, the transmission electron microscope and the field emission electron microscope. Later we'll discuss about that. Suara saya jelas ke slow sangat?
Jelas, Doktor.
Jelas.
Right, good. You know, because we couldn't observe them, and you'll see that nature doesn't fit into our neat classical boxes because our brain, we could only observe the classical boxes, classical physics, not quantum mechanics. Because that's why they are quite mind-bending. And third, you should be able to relate matter waves to electron behavior in solids. So electron will behave differently in solid, in liquid, in gas, in plasma. So you should be able to relate them. So this directly connects to the cost outcome number 1. You can see from the slide. Where is the cost outcome number 1? This one. This is the cost outcome. Anyway, if you click the link that I have given to you, can you access this slide? Boleh access tak?
Boleh, Doktor.
Boleh? Okay, good.
Boleh.
Good. So course outcome number 1, where we are learning about wave propagation. Wave they are moving. They could propagate from one part to another part of the crystals, from another part of materials. They propagate using the wave, is sinusoidal wave or cosine wave, the proton, electron, neutron, through the crystal lattices. So on the right hand side of the slide, so look at our chapter scope. We have two main topics. So section 1.1, it's specifically for de Broglie wavelength. Section number 1.2, we have the wave and particle duality of matter and light. So according to your student learning time allocation, you have 3 hours of face-to-face lectures or online lecture for this the whole 3 weeks. Oh ya, nanti kita ada masalah. Kita ada kelas kita di Selasa dan Jumaat kan? Kelas kita Jumaat tu raya tu. Takkan lepas dengar khutbah raya nak dengar khutbah saya kan? Macam mana? Later we discuss lah kan? Next week kan raya? Next week Yalah, next week. It's the final 10 days, last 10 days of Ramadan. Next week, later we discuss lah. 10 days, betul lah. Final, peserta terakhir. Nanti discuss macam mana kita nak ganti kelas raya tu. Adakah saya rakam lecture ke? Ataupun kita buat kelas juga ke? So, later I put a poll, you guys need to vote. What should we do for the next Friday's class? So now, that's what we are doing now. Today, 2 hours on a lecture. And plus 3 hours of guided learning using your own time. You need to reread the materials that I have supplied to you. Infografik saya bagi semalam quite erroneous. Saya akan update lah. Ada beberapa graph that the PDF is not showing. I don't know what happened. Later I will update the infographics. Because quantum physics you cannot read, you need to see, because that's how most of the people's brains works. You need to see with imagine to understand things. This is not English literature. Even English literature also I'm having very hard time to understand heavy English literature. Just to say that you're lazy to go to the bathroom, it took about 1 page of English literature to emotionally attach you to that movement from your bed to the toilet. So anyway, so I'll give you the specific activities at the end of the session. Later I'll give you specific activities. And this chapter aligns with CO number 1, the course outcome number 1, applying basic knowledge of electron wave propagation in crystals. Movement of electron. It's important. The electron doesn't move. The bulk material will behave differently. If the electron moves very fast, the bulk material also behave differently. That's why you see some materials, they could conduct electricity, and certain materials, they couldn't even conduct electricity, and certain materials, they could initiate electricity. They will behave differently depending on the movement of electrons. The electrons that we cannot see, they don't move, your material will behave differently. They move fast, they behave differently. So it's all about the movement of the particles that we cannot see, but we could observe using spectroscopy or electron microscopy. So everything we learn here fits directly into understanding how electrons move through the crystal like this of your materials. So we move on to historical context, the classical physics crisis. To appreciate the quantum mechanics, we need to understand why it was necessary in the first place. Let's go back to the late of 1800s. Pada tahun 1800-an. Okay? And by the late of 19th century, physicists, we are not physicians, we are physicists. Physician tu doktor perubatan yang yang kalau you pergi hospital dia bagi sakit apa, whatever sickness, they will give you Panadol. That's a physician. We are physicists. Yang salah sebut, ada story saya dulu sebut I'm a physician. No. We are physicists. So physicists thought they had figured out everything. In the 19th century, using the classical mechanics, they thought they had figured out everything. Newtonian mechanics explain motion, the F equals to ma. F is force, M is mass, A is acceleration. What else? What is theory of electromagnetism? The Maxwell's electromagnetism explain light and electricity. Physics seemed essentially complete in 1900. And Lord Kelvin famously said there were only two small clouds in horizons. Those small clouds turned into a category 5 hurricane that destroyed classical physics eventually. Start with the Lord Kelvin. Look at the black body radiation in this slide. So problem number 1. When objects get hot, they'll glow. For example, your stove element, or your exhaust of your race car. What else? Hot and glowing. The sun. Apa lagi hot and glowing? And I need one more example. Hot and glowing. White star. Okay, white star. Yeah, Ilhan. Yeah, white star. Piece of heated metals. Okay. And classical physics predicted that hot objects should emit infinite energy at ultraviolet frequency. This is what classical physics has taught us. But obviously that doesn't happen. Tak berlaku pun. Hot objects doesn't emit infinite energy at ultraviolet frequency at all. Classical physics, they say hot object, they will emit infinite energy at ultraviolet frequency, but it doesn't happen. So classical physics cannot explain the black body radiation. Your toaster doesn't produce ultraviolet frequency, no. Your toaster, it's burning hot, and they are glowing, they're hot, but doesn't produce ultraviolet, which is dangerous for human. It doesn't produce. But classical physics say that they should emit ultraviolet. No, it doesn't emit. That's why we call this as ultraviolet catastrophe. The failure of classical physics, number 1, cannot explain black body radiation because hot metal doesn't produce ultraviolet frequency, doesn't produce ultraviolet light, doesn't emit ultraviolet light. So this is the failure of number 1 of classical physics. Refresh. I'm telling you that why we need to learn quantum physics. Number 1, because classical physics cannot explain small things. For example, the wavelength of light cannot explain by classical mechanics. We need quantum mechanics. So look at the photoelectric effect, the number 2, the second. Okay, photoelectric effect. So here's another puzzle. Photoelectric. We shine light on metal. Any light. Cahaya keimanan ke, cahaya lampu sulur ke, cahaya matahari ke, shine light on metals. And electrons will pop out. You cannot see electron, but you could inspect using multimeter, or you could see there will be spike of electricity. Indicates that certain electrons pop out. That is actually the photoelectric effect. From photon, photon, light is being absorbed by the metal, and the metal emit electrons. That is photoelectric. So pop out electrons, they will create electricity. The electricity created by upon absorption of light. But here's the weird part. Classical wave theory said that the brighter the light, the more energetic electrons that you could get. Kalau classical physics cakap, kita terangkan lagi light tu. Lagi banyak elektron akan pop out, akan terhasil. But it doesn't happen. So the classical physics wrong again. Kita tak boleh pakai classical physics untuk menerangkan tentang particles, the photon. Photon also particles, photon, the light, it's also particle. So classical physics cannot explain this. It's wrong. So, apa yang betul? The energy of the ejected electrons depends on the frequency of light and not intensity. Tak kira lah berapa terang dia punya light tu, kalau frekuensi dia tak cukup untuk tendang elektron from metals, we cannot get an increment of excited state electrons. Electricity yang generated also tak akan meningkat dia punya jumlahnya. So how do we change frequency of light? So frequency of light directly correlated to the color of light. So if you look at the rainbow spectrum, not LGBT, I mean the rainbow spectrum of light. You have the red, orange, yellow, green, blue, indigo, and violet. You have 7. So starting from red color of light. We are talking about light, not pigment. Pigment and light, they are different things. Pigment tu macam yang you main watercolor tu kan, itu pigment. Light from any sources. From black body radiation resources, you could get red, orange, yellow, green, blue, indigo, and violet. Starting from the light, from the red light has the smallest energy. Go to the other side of spectrum, we have violet. Violet has the highest energy, and this energy correlated to frequency from E equals to C over lambda. H is the Planck constant, C is the speed of light in vacuum, lambda is the wavelength of the light. So different color of light, they have different wavelength, wavelength of light, they have different frequency. So if light, the violet, you have violet, you have red. If we shine red light and violet light onto metal, so now my question is, which light most probably could give you more excited state electron? Is it violet or is it red? The keyword is frequency and wavelength. Which one? I need answers. Cepat sebelum saya main TikTok. Kena ada orang jawab belum kan? I need answers. I give you 1 or 2 minutes to think about it. You can use the Gemini. Kalau dah ada yang jawab.
Sir.
Yes.
Ultraviolet because it has high frequency.
Come again.
Ultraviolet because it has high frequency and low and shorter wavelength.
Good. True. But saya betulkan sikit tadi saya tanya bukan ultraviolet tapi violet. But anyway, it's true. It's true. Okay. Let's say you have ultraviolet and red light. You shine onto a piece of metal. The surface of metal that has been exposed to the ultraviolet light will have the tendency to excite more electrons. Because why? Because ultraviolet has higher energy than that of the red light. And the frequency also higher, the energy is higher, the wavelength is shorter. Higher energy is being absorbed, of course. The more easier the electron can be excited from a metal. Like that. That is the concept. That is correct. Siapa tadi? Saya lupa tengok nama. Tadi siapa bagi jawapan? Ideal. Alright. Thank you, Ideal. Right. Kat mana tadi ya? Oh, number 2. Okay, number 2 kan. Right. So, that is problem number 2. Problem number 3, where classical physics failed. The atomic line spectra. Konsep ni dia konsep spectroscopy. So, when you heat hydrogen gas, and look at its light through spectrometer. You heat hydrogen gas, you will have different color, and you cannot quantify the color using your naked eye. Just like my eye is not the same, just like my wife's eye. My eye only can see blue in color. This close blue, this one is blue, that one is blue, everything is blue. But my wife can see, oh, this is teal, this is biru biji kundang, this is royal blue, this is biru kelabu tai kucing, whatever. So if we want to quantify things, we cannot use our naked eye because different people, they will give different opinion about the color. That's why we need specific instrument. For example, we need spectrometer. When you heat hydrogen gas, they will behave differently. They will have specific color. We need to observe the light of the gas through spectrometer. And eventually, you didn't get a continuous rainbow color. You cannot get the red, orange, yellow, green, blue, indigo, and violet. Instead, you get discrete, sharp, specific wavelength. Patutnya macam cahaya daripada cahaya Kalimantan, we get spectrum kan, red, orange, yellow, green, blue, indigo, violet, kan. But if we specifically look at the atomic line spectra of hydrogen, we cannot get that rainbow. We only get sharp line at specific wavelength. This wavelength, one line, another line. Very discrete. You can see the lines one by one, but why? So from Rutherford's model, he said that electrons orbit the nucleus. Rutherford, yang model atomic model yang you belajar maybe during the form 5, the SPM, earlier age of SPM. Rutherford model looks like electrons orbit the nucleus like planet. It's like planetary system. But according to Maxwell equation, accelerating charges radiate energy. Accelerating charges, I mean the electrons, whenever electron is moving around the orbit, they are accelerating because they are always changing their direction. So they are accelerating. So accelerating charges radiate energy. So an orbiting electron is constantly accelerating. So it should continuously lose energy and spiral into the nucleus about a nanosecond. Atom, electron, bergerak. This is the Rutherford model. This is classical physics. Classical physics, Rutherford model. Yeah, electron, bergerak, pusing, orbiting, and electron. According to Maxwell equation, also classical physics, accelerating charges, the electron is moving. Even though it has steady speed or steady speed, but the direction is always changing. Due to that, it is accelerating. And accelerating particles, they should continuously lose energy, and finally, they will be stuck into the nucleus of the atom. Whenever the electron is stuck into the nucleus of the atom, the electron is not stable, it's unstable. Dia akan musnah. But this doesn't happen because atoms are stable. Atoms exist. Atom exist. Kalau atom tak exist, kita tak wujud. So again, this classical physics fail to explain this. They have no answer. And about the spectrometer, if you don't understand right now, never mind. We will have a specific chapter for that. Or you could use the Gemini function. Tak masalah. I would not ask this anyway, but for you to understand, you should be able to search materials that could give you solid explanation about the Rutherford model and so the hydrogen atomic line spectrum. So these 3 failures cukup lah sudah. 3 failures cukup. Kali keempat fail kita percaya memang dia tak okey lah kan. So these 3 failures, the first one is black body radiation. Second one, photoelectric effect, and the third one is atomic spectra. So they were the crises that demanded completely new framework, cannot use classical mechanics. And that framework becomes the quantum mechanics. Only quantum mechanics can explain not just these three failures, tons of phenomena of quantum realm. We need quantum mechanics. So think about this. The theories that had successfully explained everything from planetary motion to electromagnetic waves completely fail at the atomic scale. They cannot explain the atomic scale, the small world, they cannot explain. So this should make you humble about your current theories. Perhaps they too will one day need revision. Any theories? We as physicists and scientists, we don't dare to say that this is the ultimate theories. It can explain everything. No. Even the latest theory that we have discovered yesterday also, that's not 100% the truth. So what is the truth? Only God knows. So later, after we have passed away, we can ask God. So what is the truth? We can learn later. But here, in this world, we keep on learning, trying to find out any theory that is the closest to the truth. Right? So I go slow sedikit lah sebab ni konsep sangat penting. Now, look at the third slide over here, the quantum revolution, the key experiments and ideas. So we have 1, 2, 3, 4, and 5. Max Planck, Albert Einstein, Niels Bohr, Louis de Broglie, and Wilson Germer. Let's see how brilliant minds solve this crisis. These 5 legendary physicists. It happens roughly around 1900 to 1927, about more 100 years or so ago. So in 1900, Max Planck, Max Planck solved the black body radiation problem by making desperate assumptions. He said energy comes in discrete packet. Energy from the photon, from the sunlight, comes in discrete packets. It comes from a bundle, a packet of known as quanta. Quanta comes from the word quantized. Packet, a packet of angpau. Packet of angpau kita buka. Oh, dapat RM10. Okey lah. Okay. Oh, dapat RM5. Tuan rumah kena kot. Quanta, quantized. We could quantify. Quanta means quantify, comes from the quantify. Quantify means we could count. So energy comes from discrete packet that we could count the value of that energy. How do we count? How do we calculate? From E equals to hc over lambda. E is energy, the energy that is being carried by the light, equals to hc over lambda. H is a Planck's constant. C is the speed of light in vacuum. Lambda is the wavelength of the light. So at first, he thought it was just a mathematical trick, but it wasn't. So he discovered energy quantization accidentally. So he discovered energy quantization, which could calculate the energy of light, which classical mechanics failed. So in 1905, the next milestone, Albert Einstein took Planck's idea. Planck studied it. Einstein took and seriously studied it, and finally he could explain the photoelectric effect in the previous slide, which classical mechanics failed. So Albert Einstein managed to explain the photoelectric effect using the concept of quanta of light, using the light packet E equals to hc over lambda. Of course, Albert Einstein is famous from the equation of E equals to mc square, kan, which he used that to accidentally discover the atomic bomb. Accidentally, I don't know. Only God knows. And he proposed that light itself comes in particle-like packets known as photons. So each photon carries energy E equals to hc over lambda, or E equals to hf at its frequency, and frequency is equals to c over lambda. So if the photon's energy, which depends on frequency, is high enough, it can knock out an electron, as I mentioned before. Tadi apa, siapa nama tadi? Idlan. Sorry, saya lupa. Kan cakap.
Ideal.
Ha? Apa nama dia?
Ideal.
Ideal. Ideal jadi idli pula. Tahu lah saya tengah lapar. Aduh. Okay. If the photon's energy is high enough, it can knock out an electron in any material that has absorbed that photon. Because photon carries energy, and the amount of energy can be calculated using E equals to hc over lambda. The higher the frequency or the higher the energy, most probably the electrons of the material will be kicked out easily. So more photons mean more electrons, but each electron's energy still depends on frequency, the frequency of the photon. So this was revolutionary. Light, which we proven was a wave through the interference experiments. We have done this before, interference experiment during your secondary school, I believe. Also behave like particle. So Einstein actually won the Nobel Prize for this, not for relativity, Einstein is famous for the relativity, but he won Nobel Prize not because of the relativity, but for this quantization of light. E equals to hc over lambda or equals to hf. Dia menang Nobel Prize. Dia punya thesis untuk PhD dia pun, saya rasa tak silap saya 24 pages only. Kalau thesis undergraduate yang you buat nanti kan 24 pages, saya rasa kena baling ke tong sampah. But Einstein did defended his PhD thesis for 24 pages. Different breed. So next to 1913, Niels Bohr tackled the atomic spectra problem yang tadi disebut problem number 3. He tackled the atomic spectra problem. He said electrons can only occupy specific orbits. Electron dia bukan orbiting the nucleus like planetary system, but electron occupy specific orbit. Dia bukan macam orbiting, kan? Dia occupy specific orbit. Ada certain orbit dia akan duduk, certain orbit dia tak duduk. So electrons can occupy specific orbits with quantized angular momentum, and electrons can jump between this orbit by absorbing or emitting light at specific frequencies. This explains hydrogen's line spectra perspective. Nanti kita akan belajar macam mana elektron boleh lompat ke atas, excitation, elektron boleh turun ke bawah, relaxation, or electron being transferred to another orbit known as Foster resonant energy transfer. We will learn that later. Tak apa, sekarang ni untuk tengok jargon saja. But Bohr model was an ad hoc. The ad hoc Bohr model, okay, atomic Bohr model. He just imposed quantization rule without deeper justification. It worked for hydrogen. Dia boleh terangkan apa spectra for hydrogen, but fail for more complex atom. For hydrogen apa? Helium. He failed to explain helium atomic spectra. He only can explain hydrogen. Sebab dia very ad hoc. Now move along to 1924. About 11 years later, Louis de Broglie, he made a big leap. That central to our chapter. De Broglie starting point. Orang tadi daripada Max Planck, Albert Einstein, Niels Bohr, tak berapa nak meluas lagi. Then comes Louis de Broglie. So he asked, if light waves can behave like particles or photons, Not proton now, photon. Photon is light particles. Can particles behave like waves? This was his question. If light waves can behave like particles, can particles behave like waves? That was the question. And he proposed that all matter has a wavelength given by lambda. And from his idea, lambda is equal to h over momentum. Lambda equals to h over momentum. H is Planck constant. Momentum is the part of particle. We are learning wave particle duality. Lambda is wave part of the particle. Momentum is the solid part of particle. So lambda equals to h over is a equation that connects wave and particle properties of small matter. For example, the photon also can be used for proton, electron, and neutrons as well. So lambda equals to h over momentum, or you can say h over p, doesn't matter if you like it. So a moving electron should act like wave. And this was his PhD thesis hypothesis. Louis de Broglie punya hypothesis, his PhD hypothesis. Most people thought it was crazy, but if true, it would explain Bohr quantization, where the electrons in atoms are standing wave, like waves on guitar string. Guitar string kita tekan, dia akan standing wave. Kita nampak wave tapi dia tidak bergerak, standing wave. Only certain wavelength fits at certain chords. If we press the standard tuning, E, B. Esok aku beli gitar baru. Yalah. Tak tahu, kita tak belajar music. So look at the final milestone, 1927. We have the Davison German. So they fired electrons at nickel crystal and found diffraction patterns, interference, just like waves. So the de Broglie was right. Particles are waves, or rather, quantum objects are neither classical particles nor classical waves. They are something entirely different. They are particles and waves together. They could see interference. So the timeline shows one science greatest triumphs in just 27 years. 1900 sampai 1927, in just 27 years, physics was completely revolutionized. Besides classical physics, before 1900, we have classical physics. In 1927, we have quantum physics. And this revolution directly leads to understanding materials at the quantum level. I mean, the concept that could be used for small particles, which is why you are here studying material technology, and so this is solid state physics. And next, course roadmap, chapter 1 review. Saya bawa slow sikit. I think we should stop at 9:55. 9:55 we will stop. Before we seriously looking into the mathematical side of solid state physics, let's see the chapter number 1 fits for the bigger picture. The course has 7 main chapters. They build logically for chapter number 1, where we are now, the quantum basics. When we go to Schrödinger equation, Schrödinger, ada cakap Schrödinger, ada cakap Schrödinger, never mind, just say whatever you like. And this is the fundamental equation governing quantum behavior. To understand the quantum behavior of small particle, we need this equation that could explain most of the behavior. Then in chapter 3, we try to learn to solve Schrödinger equation in one-dimensional particle boxes, one-dimensional things. One-dimensional things, for example, one dimension dots. It's quantum dots. And two-dimensional things, for example, like this thing, we have nanosheets. Kalau ni bersize nano, we call this nanosheets, two-dimensional particles. What else? Chapter number 4, we will learn reciprocal lattice, crystal vibration phonon, so on and so forth. And finally, at chapter 7, we will learn energy band. This is very important because by understanding chapter 7, you could understand semiconducting materials, which still are relevant in our industry in Malaysia and worldwide. We're still using semiconducting material in every electronic materials, electronic gadgets. So chapter 1 is foundation. We established that electron in your materials don't behave like tiny particle. They are waves propagating through the crystal lattice. So by understanding this movement of electrons, we could predict, we could observe, we could calculate the properties of any materials that we have on the planet Earth. Planet Earth, dekat planet lain, we don't know what kind of material. Maybe they don't exist in our periodic table, but they exist in different periodic table. We don't know in different planets. So it's a key refresher. Look at this wave, the sinusoidal wave diagram. So we have the amplitude, the maximum displacement. The maximum displacement for sound, this is volume. The amplitude. For sound, this is the volume. For light, the amplitude is the brightness. For matter waves, we see it as related to probability. Again, for sound, the amplitude is volume. For light, it is brightness. For wave matter, it relates to probability. Probability of what? Probability of the particles to exist. As I mentioned before, electrons could exist at certain orbits. Doesn't move in circular motion, but it only exists at certain orbits. And the probability of an electron to exist at certain orbit can be calculated using this amplitude because it relates to its probability to exist. Hear me out. This is just a jargon first before we turn into the equation. What else? The lambda, the wavelength, the lambda. It's the distance between successive crest. From the first crest and go to the second crest. This is one lambda, one complete wavelength, one lambda. So it's measured in meters, nanometers, or for atomic scale waves, meter or nanometer. Then we have the frequency, the oscillation per second, measured in hertz or per second. And high frequency means rapid oscillation. Then we have period, the time for one complete oscillation. So period is t equals to 1 over frequency. What else? We have phase, or the symbol is phi, mana phase? Ni phase. Saya tak tahu lah, you nampak tak saya punya cursor ni? Boleh nampak ke cursor saya? Boleh nampak ke cursor?
Boleh.
Okay, good. Nampak cursor. Okay, bagus. This is phi. Yang ni bukan tongkat setan. Ini ada nama lain. Tak apa, kita tengok phi pun. Ini phi. Phi is where the wave starts. Two waves can be in phase, which the crest align. This is the starting point of wavelength. They are aligned. It means that they are in phase. So when they are in phase, the angle is 0. Or out of phase, different. I mean the wave doesn't coincide. They differ a little bit. So the crest meets trough. For example, this is how noise cancelling headphones work. Crest, when the crest meet trough yang kat bawah ni, yang lekuk ke bawah means trough. Crest adalah lekuk yang kat atas. Kalau the two waves out of phase, crest meet trough, this is how noise cancelling headphones works. So I think I have to stop right now because it's 10:53 already. Maybe have some other lecture to attend. So we will continue on Friday. Friday kan? Ke Thursday?
Friday.
Friday. Yeah.
Saya nak cadangkan tukar time tu boleh ke?
Kalau
Sebab
semua
saya dah check dah tadi jadual semua orang. Selasa pukul 8 sampai 10, lepas tu Khamis 11 sampai 12 macam tu.
saya tak boleh pukul 8.
Selasa tak boleh 8
Tak boleh. Sebab semester ini, start tahun ini, anak saya bersekolah 3 sekolah berlainan, berjauhan, jadi saya tak sempat pukul 8. Sebab takkanlah saya hantar anak saya pukul 6.30 pagi kan. Sekolah buka pukul 7. Jadi daripada tempat saya tu nak ke sini, saya tak sempat pukul 8. Anak pertama drop start pukul 7. Anak kedua sampai kat sekolah dia 7 suku or so drop dia. Anak ketiga 7.30 sampai. Jadi daripada Tanjung Lumpur tu nak sampai ke sini saya tak sempat setengah jam. So tak sempat. Habis tekan minyak pun saya tak boleh sebab saya akan terpur jam dekat 4 tempat. Saya tak boleh nak buat laju. Jadi pukul 8 tu very risky lah. Tak dapat. So think again, try to discuss with your friends. Tengok kalau nak tukar jadual, kalau semua orang setuju, saya okay. Tapi 8 AM definitely I cannot lah. The earliest is 9 AM. Begitu. Alright, so I need you guys to try to discuss first in WhatsApp group or whatsoever. So we continue our lesson on Friday. Okay, that's all guys. Thank you very much for your attention. Nanti saya
Thank you, Doktor.
upload recording nanti.
Thank you, Doctor.
Thank you, Doktor.
Okay. Okay.